Okay, so this is going to be a video about just some acid-base problems, how to solve them, how to understand what they're asking of you. So, paper one, multiple choice. So the way this is set up is it's going to be paper one stuff and then paper two, and then HL at the end. So this is a question pulled off an old exam. So which substance can be dissolved in water to give a 1 molar decimeter cubed? This doesn't really matter, this number here. The key points in this problem are this. Solution with a high pH, so that means I'm looking for a base, and a high electrical conductivity, meaning I need a strong something. So with these two bits of information, I know that I need a strong base, which is going to be NaOH. So your answer here would end up being D. This is a base, but it's weak. Because of that, that's wrong. This is pH neutral. It's a salt made out of conjugate acids and bases that were strong. So this was made out of HCl and NaOH. So their conjugate acids and bases are weak. So this would give you high electrical conductivity because it's ionic, but excuse me, but it's not going to have a high pH. And so another possible answer would have been this guy here. So this is going to have high electrical conductivity, but this is going to be a very low pH, and because of that, this guy's wrong. Cool, so here we're looking at 4 different aqueous solutions. We've got, we've got 2 acids. These guys are acids. And 2 bases. If you don't know very common acids and bases, so for example HCl, HNO3, or H2SO4, if you don't know these acids yet, these are common acids, you need to memorize them. Same with very common bases like NaOH. They could do LiOH or NH3. These are all common bases. Need to have these memorized. So anyways, I got acids and bases, and we're trying to get these in order of increasing pH, so I want lowest first. So what that means is I'm going to pick the acid with highest concentration, and then I'm going to move on to the base with the highest concentration. So I've got this acid, and it's going to have a highest concentration, so that means I've got to have 1 first, and then I've got an acid with a low concentration, 2. This base has the highest concentration, so that's going to have the highest pH, so that's going to be last. And then I've got a base with the second lowest concentration. So our answer should be 1, 2, 4, 3. There it is. All right, so now we're going to start to move on to weak acids and bases. I just said before that NH3 is a common base, so I'm going to do common base. So therefore, NH4 plus, like you'll see here and here, is going to be a common weak acid. Sorry, this is a weak base as well. So what that means is if we have a solution of just NH4 plus, it's going to have a pH lower than 7 because it is a it is an acid. It's just going to be weak because it's a conjugate acid of this base. So these guys go back and forth. This is the base. This is the conjugate acid. Since it is a conjugate acid, then it's going to be acidic, hence the name acid. Another thing that would be really helpful to remember is CH3COOH. This is ethanoic acid. That's going to be a weak acid. Can go back and forth to CH3COO minus. This is ethanoate. And since this is a weak acid, this must be a weak base. Same logic as before. This is, sorry, let's change colors. If this is an acid, therefore this is a conjugate base. Same logic. So I've got ammonium chloride. This is going to be acidic because Cl is a spectator ion, and we just talked about how ammonium, the NH4, is an acid. I've got NH4COOH, so this is going to be weak acid and weak base. We don't know what the pH is going to be, but we know they're probably going to cancel each other out. It's going to be somewhere close to 7-ish. And then last thing we have is sodium ethanoate, or NaCH3COO. And since this is the weak base, that means this is going to be basic. So finally, what I'm going to look at here is, I know NH4 is acidic, so this is going to have a low pH. I know this is going to be somewhere around 7 because they'll cancel each other out, and this is going to be a high pH. And then we have constant solutions, so that doesn't, sorry, constant concentrations, and we're looking for increasing pH, so low to high. So they happen to have it all in order for us. So it should just go, 1, 2, 3. And there we go. It's not so hard. Conjugate acids and bases. All right, so which is a conjugate acid-base pair in the following reaction? So I've got HNO3, and I'm going to use this NO3 because we are going to be moving protons left and right. So I'm going to use NO3 to track the molecule. So I know that these guys go together. It gained an H, so that's a base, which makes this a conjugate acid. And if that's how that one works, then this must be the acid, and this must then be the conjugate base. So these guys will pair up. So now we just got to pick the right pair. Nope, those are different. This is one possibility. Let's check to make sure the rest are wrong. These guys don't match. These guys don't match. Therefore, it's B. Okay, which one of the following species can act as both Bronsted-Lowry acid and base? So we are looking for something, so if it's an acid, it needs to have an H to donate, and if it's going to be a base, it should be negative or have a lone pair of electrons. More often than not, this is what you're looking for, the negative part. So based off of these two things, we can get rid of this because there's no negative. There's not a negative charge at all. We can get rid of this because there's no hydrogen plus to donate. And then we're down to C and D. D is it's water that has been deprotonated. So D comes from this business, the autoionization of water. And this never loses a proton. And since that's the case, we can get rid of this. So our answer would be C. Acid reactions with compounds. Okay, so which of the following is/are formed when a metal oxide, so we would do, I'm going to just pick one, like MgO, that's a metal oxide, reacts with a dilute acid. So they didn't say if it was strong or weak, so what I'm going to do then is just make up an acid that works for me. I'm going to just do HCl. So based off of this, I'm going to end up needing 2 of these because magnesium is 2+ and chlorine is a minus. So that gives me, remember the metal and the non-metal part of the acid are going to react. So I end up getting myself MgCl2, and that only leaves me with the H and the O. And if you haven't caught on yet, H and O love to get together and make some water. So then what I end up with is a salt. Oh, let's do that in blue to make it more clear. So what I end up with is a salt. Remember, a metal and a non-metal, an ionic compound is a salt. And this is water. So in summation, I get this, and not hydrogen gas. This is when you have a metal and acid. This is a metal oxide, so this is not going to be right. So I'm left with 1 and 2 only. Paper 2. Okay, so I know you can't read this, don't panic. I just wanted to show you how long it was going to be to start. So this looks like it's going to be a 3-part question, A, B, and C. So now, here's part A of it all. The value of the ionic product constant of water, Kw, super nice to know that's what they're talking about, at 60 degrees is this. State the Kw expression, meaning no numbers, for Kw. So Kw is equal to the concentration of H plus times the concentration of OH minus. There's our 1 mark. Sweet, got it. If you're confused, where this is coming from is the autoionization of water. So it goes back and forth to this. This is a liquid. This is aqueous, and this is aqueous. And this all stems from an equilibrium constant, where we do the concentration of the products over the concentration of the reactants. And we never use liquids or solids. So if we were doing this for this equation, we would end up with the concentration of H plus times the concentration of OH minus, not including, we would not include water in this because it's a liquid. So if we were talking for just Kc, we'd get this, but we end up getting, they say Kw because why not be more specific? I don't know why they do this. Doesn't matter. All right, so now calculate the values of H plus and pH. So I'm going to just do this negative log concentration of H plus right there in water at 60 degrees Celsius. So they give us the Kw, and we just wrote the expression. So we're probably going to end up using both of these. Remember, these paper 2 problems are built to scale up. So whatever you get in A most of the time, you're going to use in part B, and whatever you get in part B most of the time, you end up using in part C, and so on. So I've got Kw equals H plus times OH minus. I know the Kw is 5.6 times 10 to the negative 14 equals these things. And since these are going to be equal because they're formed in equal ratios, I'm going to just call it H plus squared. And the reason why I'm doing this is because the concentration of H plus is equal to the concentration of OH minus. So I'm going to just substitute this in for OH minus. And H plus times H plus is H plus squared. So then I'm going to go ahead and do the square root of both sides. And I end up having to pause right now because I don't have a calculator. I'll be right back. All right. So I did it, put it in my calculator, and I get the concentration of H plus is equal to 2.37. Yep, okay. Times 10 to the negative 7. Mole decimeter cubed. The reason why I had to stop to think is because I've got 1, 2, 3 significant figures, and I just wanted to check it up against the value they gave me. So I'm making sure my significant figures match their significant figures. And then now, so there's the one part, and now I need to do pH is equal to the negative log of the concentration of H plus. Negative log answer, and I get pH is equal to 6.626. Oh, Mr. Parks, why don't your significant figures match? Whenever you're doing a log, so whenever this happens, significant figures count, oh, that's not going to fit. Significant figures only matter after the decimal. Which is why I used those 3. The first 6 doesn't count because it's just describing the power that it's at right now. Cool. So you probably, if you're wondering, you probably would have ended up getting, what's a color I haven't used yet? This would have been 1 mark, this is 1 mark, and then this is 1 mark, and that's where your answer of 3 comes from. So you got to show your work. So then this is the final one. So the value of OH minus in water is greater than the value at room temperature. Explain why water is not alkaline at 60 degrees Celsius. So basically what they're saying is this. You found out the concentration of H plus was equal to 2.37 times 10 to the negative 7. And then you also know that the concentration of OH minus is equal to 2.37 times 10 to the negative 7. So they're hinting at this. If you did the pH of this, you would find out that the pH is going to be actually a little bit higher, or sorry, if you did the pOH, it's going to be not 7. So what they want you to understand is that since these are both occurring, water is neither acidic nor basic because they occur in equal proportions. Proportions. Therefore neutralizing each other. Oh, that's not a C. Oops. Dang it. Erased the wrong thing. Let's go back and fix that. Each other. It's kind of a long explanation. I think you could get away with less of the words that I used and still get the 1 mark, but I'm trying to give everything in the most detail possible right now. Cool, so there's one of our paper 1 questions. Oh, this looks like a new paper 2 question. This is only a 1-parter and it's for 4 marks, which means oh fun. So define the terms strong acid and weak acid. So I'm already thinking that's 1 mark and that's a 2nd mark. Using hydrochloric acid and ethanoic acid as examples, write equations to show the dissociation of each aqueous solution. Okay, so strong acid is a proton donor that dissociates completely or fully. Weak acid is a proton donor. Remember, they're both acids, so they both have to be proton donors. That dissociates partially / is at equilibrium. All right, so then I'm going to color code these. My strong acid is going to be this, so HCl, and they want us to show in aqueous solution. Okay, so the fact that they say aqueous solution, I'm going to panic because I don't know if this is important or not, and just do this, H plus Cl minus. And then my weak acid I'm going to do in green. And ethanoic acid, remember 2 carbons, so that means it's going to be CH3COOH. This is one of those common acids that I told you guys to memorize earlier. CH3COO minus plus H plus. The key here is this. Equilibrium. Since it's a weak acid, you need to have the equilibrium. And I forgot to put my states in, so I'm going to do that. So you got to put it at equilibrium because that's what makes it a weak acid. So then I'm thinking that the equations are going to be worth a total of 2 marks. So 1 here, 1 here. Final paper 2 example. It's a 4-part challenge. So if you want, take a minute, pause, cry a little bit, get some coffee, come back, and then go at it again. All right, so calcium carbonate, CaCO3. A good way to remember carbonate is if this is carbonic acid. And then remember, whenever you cut off the protons of an acid, it turns into like an 8, carbonate, ethanoate, something along those lines. So then the CO3 2 minus is going to be carbonate. All right, calcium carbonate is added to separate solutions of hydrochloric acid and ethanoic acid of the same concentration. State 1 similarity and 1 difference in the observations you could make. I hate these questions because I never know what they're looking for. So what I do know is this. CaCO3 plus 2 H pluses gives me Ca2 plus H2CO3. And also H2CO3 goes back and forth to H2O and CO2. This is a gas, therefore bubbles, or they like the term effervescence. You should check that spelling, because Lord knows I spelt that wrong. Bubbles will be produced. You could write it as in two different ways. So you could do this series to justify the bubbles being made, or you can just kind of put it all together. So CaCO3 plus 2 H pluses, so 2 acids, gives me Ca2 plus H2O plus CO2. And all I did there was substitute, since these are in both equations, I just substitute this in for the H2CO3. So the similarity, both will produce gas. The difference, HCl, that's what we're talking about, right? Yeah, this is HCl. And then this is CH3COOH. HCl will bubble. Come on. Struggling with my pen. Will bubble more vigorously because it is a strong acid. I think you can just leave it like this. They're probably not going to want you to describe why ethanoic acid doesn't bubble as vigorously. I'm going to explain it anyways. Since ethanoic acid is a weak acid, so what's going to happen is CH3COOH is at equilibrium. CH3C, it's not a C. COO minus plus H plus. So the reason why ethanoic acid doesn't bubble as vigorously is because you're waiting on this weak acid to undergo Le Chatelier. So we're waiting on Le Chatelier to create more H plus, therefore slower rate of reaction. How convenient of a second question is this? Because I used it literally to explain the logic behind the last one. So we know calcium carbonate, that's not big enough. CO3, hydrochloric acid, HCl. I'm going to just smash these guys together. HCl plus CaCO3 goes to CaCl2 plus H2O plus CO2. Cool. There's 1 out of 2 marks. Need to remember to balance. Yeah, cool. Now we're good.
All right, guys. It's important to understand the final paper 2 question. Yeah, looking at part 3. So when we have this following question, determine the volume of 1.5 mole hydrochloric acid that would react with exactly 1.25 grams of calcium carbonate. We have to do the following procedure.
Okay, so he doesn't know that we're not going to cut, and I'm going to just take over from here. So remember, you got to do grams to moles, and this is really just a big stoichiometry question. So I'm going to put Oops. God, I hate writing. I'm going to rewrite the balanced equation that we had before. HCl. We had two of these guys, and we go to CaCl2 plus H2O plus CO2. So we got to do grams to moles. 1.25 grams CaCO3. Grams CaCO3 on the bottom. And we're going to switch this to moles CaCO3. And using the periodic table, we end up getting 100.9. Or 09, sorry. Remember, you just do calcium plus carbon plus oxygen, oxygen, oxygen. Cuckoo! So then, moles of calcium carbonate goes to moles of HCl. Just struggling. And then this is, don't forget, whenever it's mole to mole, you're using the coefficients. So I've got 2.
It's really urgent.
Super urgent. I'll be right back.
Is it?
So when you do this calculation, you end up getting 0.025. Let me double check. Yeah, 250 moles HCl needed.
Yeah, guys.
So then you got to do your C equals N over V, your concentration formula. 1.0, writing so hard. 1.50 is equal to 0.0250 over V, or in other words, V is equal to 0.0250 over 1.50. Divide this by 1.5. You need 0.0167 decimeters cubed of solution. Killed it. All right, cool. Last part. We need to calculate the volume of carbon dioxide measured at that temperature and at 101 times 10 to the 5th. That's supposed to be an exponent, which could be produced when blah, 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 blah. So we're going back to our balanced equation. 2CO2 plus H2O plus CaCl2. And we're trying to switch 1.25 grams of this to moles of CO2. So then I get 1.25 grams divided by 100.04 grams for every 1 mole, and a 1-to-1 ratio of CaCO3 plus CO2. So then I end up getting an answer of 1.25 divided by 100.04. Where did it go? 0.0125 moles CO2. So now, since this is a gas and they are going to want the volume, I need to go to my PV equals nRT. R is 8.31. T is going to be 273. N is going to be 0.0125. And the pressure, I need to switch to kPa. So I get 1.01 times 10 to the second. And from here I can solve for volume. V is equal to nRT over P. I'm going to just substitute all my numbers in. I'm running out of room, so I'm going to just do this on my calculator. 273 times 8.31 times 0.0125. Divide that by... I get a volume of 0.281 decimeters cubed. Cool. That's the end of that. This last little bit was just, this is more chapter 1, but I put it on there because I thought it would be good, good review, good way to remember what we used to do back in the day. Cool. Alright, so this is HL questions. If you're SL, you don't need to watch the rest of this. I guess you never need to watch any of it, but it's a good, it was a good practice one for you. Alright, so HL questions. We're doing weak acid titration. So remember that the only difference between a strong acid and a weak acid is weak acids, they dissociate partially. If they have the same volume and the same concentration though, there's going to be the same amount of H plus available. So since there's the same total amount of H plus, it's just a weak acid is going to dissociate at a different rate. Therefore, which of these will be the same for these titrations? Initial pH, this will not be the case because a weak acid will have, so strong acid, weak acid. Strong acid will have a greater concentration of H plus than a weak acid. The pH at equivalence point, no, because as I'm going to do HWA, as this gets titrated, we end up with WA minus plus H2O. And this is going to be a conjugate base. And since it is a base, it's going to raise the pH of the equivalence point. Volume of NOH required, yes. And this is because we have, going back to our original thing, same amount of H plus, so it's going to require the same number of moles. Of OH minus. So then our answer ends up being 3. Buffer solution preparation. This is when we want some HWA and some WA minus. HWA goes back and forth to H plus WA minus. A buffer solution utilizes Le Chatelier's principle to keep the pH fairly resistant to change. So if you ended up removing some of this H plus, your HWA would dissociate more and create more of both products. Whereas the same thing but opposite would be happening if you added more H plus. So if you tried to decrease the pH, the buffer solution would just shift to the left towards the reactants a little bit more. So here we've got, first of all, we need a weak acid, and this is a strong acid, so can't be that. Cannot be that, for sure not that. So then here we go. This is a weak acid, so that's a weak acid, and it's got its proton still, so there's my HWA. Here is a weak acid without a proton, so that's my WA minus. So, and they're 50-50 amounts, which is convenient. But the key here in this one is it has to be a weak acid. That's the question they're really asking you. It's the one they really want you to remember. Propanoic acid. CH3, CH2, COOH is a weak acid. Give the equation for the ionization of propanoic acid in water and deduce the expression for the ionization constant Ka of propanoic acid. So whenever you do these, you can do it one of two ways. OH. So you can do it where it's showing the water, and water is acting as a base. And H3O plus. This is one option, or else you can just do it where it is dissociating aqueously. CH3COH. 2COO minus plus H plus. So both of these are acceptable. Since they said specifically in water, I would probably opt for this one just to play it safe. And then deduce the expression for the ionization constant Ka of propanoic acid. So Ka is equal to the products over the reactants. So I'm looking at concentration CH3CH2COO minus times the concentration of H plus over the concentration of CH3CH2COOH. So this one is different from Kw because this is aqueous and water is a liquid. So we're going to exclude water from our Ka expression, but we are going to include propanoic acid because it is aqueous. Therefore, it will have a concentration. Calculate the Ka of propanoic acid using the pKa value in data booklet. I will be right back because I need to grab a data booklet. Okay, so in the data booklet it says pKa is equal to 4.87. So just like pH is the negative, oh come on, it's the negative log of the concentration of H plus, pKa is equal to the negative log of Ka. So remember that P just means negative log of, in a way, it means power. So then I know 4.87 is equal to the negative log of Ka. Ka is equal to negative 4.87, 1.3, whoa, that's what you get for writing and not looking. Where the heck is my pen now? There we go. Erase, why won't you erase? Okay, I had some difficulties there with my pen. Now it's still not working. Maybe it's gonna work with me. Maybe not. Alright, so the pen is being obnoxious, so I'm gonna rewrite this here. Ka is equal to 1.3, about 5, times 10 to the negative 5. Cool. From your answer, from B, calculate the H plus concentration in aqueous solution of propanoic acid of concentration, blah, 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 and hence the pH of this solution. Cool. So here's what we got. Oh, sorry, itchy face. This is where you need to assume that the dissociation is negligible. So this is like the beginning of the icebox stuff. CH3, CH2, COOH, back and forth, H plus CH3, CH2, COO minus. We've got an initial change and end 0.0500 0 minus x. You assume that this is negligible because the dissociation constant is not that significant. X. So then now going back to our Ka is equal to the concentration at H plus times the concentration of CH3. I'm running out of room, so we're just going to do that over concentration CH3, CH2, COOH. And once I substitute in, I have my Ka was 1.34, 35. I don't want to try to erase because my pen's being a butthead right now. Times 10 to the negative 5 is equal to x squared over 0.050. So therefore, x squared is equal to x squared is equal to 6.74 times 10 to the negative 7th, which means the concentration at H plus is equal to, I'm going to square root both sides, 8.21 times 10 to the negative 4, which means the pH, just an obnoxious question, is going to be equal to 3.09. Ta-da! Titration question, paper 2. The following graph shows how pH changes during the titration of a weak acid with that. Cool. This is just the introductory thing so you could see it. Here come the questions. State the pH at equivalence point and explain why the pH changes rapidly in this region. So what they're looking for is you to understand that the equivalence point is going to be about the midway point of this huge peak. So it looks like at about 8, I know it's not straight. It looks like at about 8 centimeters cubed you get to a pH 9. So pH is equal to 9. And the reason why it's rapidly changing is because pH is based off of, what's it called? A base 10 system. In other words, log. And when at neutral, or when the acid is neutralized, I'm gonna erase this. Come on, pen, work with me. Nope, nope, absolutely not. Cool, it's great. I didn't want you to, anyways. It's fine. Okay, so I'm gonna just rewrite that because life is hard. When an acid is being neutralized, there is a time when concentration of H plus goes from small to, come on, to when it is neutralized to it becoming basic. This change takes very little OH minus because it is log based. In other words, since log base is base 10, it's easy to go from 1, it's easier to go from 1 to 10 to 100. So this would be easier. This is like when we're getting close to the neutral point, or the equivalence point, than it is to go from, so I'll do this up at the top since I'm out of room. So it's harder to go from like 1,000 to 10,000 to 100,000. The change is just so much more that that to get to Markstream pHs, you need to make drastic changes. Whereas when it's becoming neutral, since it's log based, you don't need that much more or that much addition of H plus or OH minus to make a drastic swing. And when it's at neutral, then we're looking, or sorry, when it's at equivalence point, then we're really just examining the pH of water with a weak base in there. So it's hard to put into words what they're looking for, but the key that they want you to talk about is equivalence point and log based. My biggest issue is that I should have probably thrown in the phrase equivalence point in there. So I would not be surprised if I only got 1 out of 2 marks on this, but that's the idea that they're looking for. All right, calculate the initial concentration of the acid. So we got to figure out how much volume. So I'm going to write out the theory before you see me struggle with the graph. Volume of NaOH needed to get to equivalence point can be converted into moles NaOH, which would equal the moles of H plus that existed in the acid. Therefore, we can figure out the moles, therefore that is moles of HA, and I know you guys don't remember this because you'd have to go back a slide, but in the beginning they told us how much volume of acid there was. So since we know volume, we can do moles over volume to give us concentration of HA. So we got to figure out the volume of NaOH needed to get to the equivalence point. I'm going to erase all of this now and start again. Alright, so now after struggling with the graph, and there's no way to show you this, you guys should definitely use a ruler. But I'm going to try my best to go straight down here. And it looks like it's just above 8 I don't know. It's hard to do on this without a piece of paper to guide my hand. So I'm going to go with 8.2 centimeters cubed NaOH, which is going to be equal to 0.0082 decimeters cubed. And if I have 0.10 mole per decimeter cubed is equal to moles over 0.0082, then I know I've got 0.0082 moles of H plus in the solution. Therefore, the initial, I gotta find what that initial volume was. 1 second. Okay, so I went back to the question and it said there was 10 centimeters cubed of HA, which then means there we've got 0.00082 over 0.010 centimeters cubed, or decimeters cubed, which gives us a concentration of, I don't want to do this right now. Not thinking about it, just going to do it. 0.082. Stupid marker. Initial concentration was 0.082 moles decimeter cubed. Nice. Next question. Calculate the H plus of the hydroxide before any sodium hydroxide is added. Use this value to determine the Ka value and the pKa value of the acid. Alright, so the H plus before anything is added is really just looking for the pH right here. So it looks like it's a bit below 3, so we're going to say initial pH is equal to 2.9. Seems good enough to me. So then I'm going to do 2.9 is equal to the negative log of the concentration of H plus. Therefore, the concentration of H plus is equal to 2.9, 0.001256. Oops, that's not what I wanted. Dang it. 0.00126. So the biggest issue with this is our significant figures, based off of my answer, are too exact. The most we could get to would be really one significant figure, but for right now, we're going to just go with it. So then we know that, okay, so we know this. We know Ka is equal to the concentration of H plus times the concentration of A minus over H concentration of HA. And we found out from the previous question that the concentration of HA was 0.082. So then Ka has to be equal to 0.00126, and I'm getting this number, just putting it in here, and it's going to be here as well because HA goes back and forth to H plus and A minus, so whatever H plus is, A minus has to be the same. So that number squared over 0.082. Then we get answer squared divided by 0.0. Oops, God, just struggling today. Ka equals 1.93 times 10 to the negative 5. And then pKa is equal to the negative log of Ka, which is equal to 4.71. Whew! It's a doozy of a question. Let's make sure we just got any of it. Yeah. Alright, looks like we answered everything. We got H plus, we got the Ka, we got the pKa. Cool, done.